to all. I am Daisy, and I will be the webinar moderator. Welcome to the 9th Masterclass Series webinar of OMS eLearning Academy. Today's webinar topic is the importance of selecting correct process analyzers. We have an overwhelming response of 60 plus registrations from 40 countries and welcome you all, and hope you all will have a very informational and interactive session today. Before we start, let me discuss a few house rules. The webinar will be 40 to 45 minutes long with a 10-minute Q&A session. You can enter your question in the chat box during the presentation, which will be answered at the end. The webinar will be recorded and available on the OMS eLearning Academy website. There will be a 2-question poll at the end for your input. Please give us your candid feedback at the end via the redirected Google form. We have 2 speakers in today's webinar. The first speaker is Dr. Suresh Agrawal, the founder and CEO of Offsite Management Systems, LLC, and Academy Director of OMS eLearning Academy. The second speaker is Dr. Ariel Kiggett, R&D and Business Development Manager at UK-based Modcon Systems Ltd. I welcome them both to speak at this educational free webinar. About our speakers' organizations, Offsite Management Systems, LLC, was founded in 1998 in Houston, Texas. It's chartered to provide consulting and refinery automation project executions worldwide. OMS eLearning Academy was founded in 2018 to provide continuing education to professionals working in the downstream refining industry and related businesses via the eLearning platform. Modcon is a UK-based company founded in 1972 specializing in process analyzers, technology, and blending control systems. OMS and Modcon have collaborated to bring their technologies to benefit professionals in the process industries. You will learn 3 ideas of the importance of selecting correct process analyzers in this webinar. 1, modes of quality analysis. 2, process analyzers. And 3, modeling techniques. Thank you all for attending this informative webinar. To appreciate your efforts, we have 2 complimentary gifts for you. Please stay until the end to learn about them. With this, let me request today's first speaker, Dr. Agrawal, to start the webinar. He will then introduce second speaker, Dr. Ariel Kiggett. I will be back at the end of the presentation. Thank you.
Thank you, Daisy, and greetings to everybody. Welcome to the 9th series of webinar, jointly hosted by OMS eLearning and also Modcon. In today's webinar, my first part, we will cover the overview of plant areas in a typical refinery and how do we estimate the product qualities, different methods, and what are the qualities of interest for products as well as components. What are different types of analyzers for various qualities, and how do we model analyzers? And then in the end, we'll summarize the presentation in this webinar. So if you look at a typical plant refinery, for example, there are 3 areas which is designated as 1, 2, 3, 4. Now, area 1 and 4 are called the fence line. It means the products coming in or component coming in and products going out. And number 2 is the tank farm, where refineries or any plant have 300 or 100 plus tanks. And number 3 is the area where actually crude oil is processed into different components. So we'll discuss the qualities in these 4 areas and different types of analysis methods available. So if you look at the fence line, to see the product and also the dispatch it is measured by lab samples or online measurement, and also is predicted by model-based prediction. Now, this model-based prediction not to be confused with analyzer modeling, and we'll discuss it to make it more clear. In the area of tank farm, it is also done by lab samples or online measurements, and also by model-based prediction. Now, model-based prediction was described in the last webinar we did. So if you want to go and view the recording, you're most welcome to do that. In the area number 3, process units, which is a stream of process units in and out, they are either measured by lab samples or online measurements, and also something called model-based or inferential prediction of the qualities of the process units. So these are the 4 areas and with different methods of analysis. Now, there are 3 methods to estimate the qualities of the products. Now, first is the process analyzer, which is the main focus of this webinar today. And process analyzer can be discrete, like for one quality, one analyzers that can be measured by multiple qualities by single analyzer like NIR and MR, and hybrid of both, discrete and integrated. And they are also multiplex. Lab analysis is a must all the time. They always do to check the values of the process analyzers and also to give a feedback to inferential model prediction. So these are 3 methods. We'll focus on process analyzer in this webinar. The qualities are measured of different products which are of interest, like crude oil, gasoline, diesel, fuel oil, bunker oil, kerosene, etc. And if you look at the left diagram, about 42 to 50% of crude oil is produced in the gasoline products, and remaining are diesel and fuel oils. So basically, about 80 to 85% of crude oil are made into products like fuel products, and they are done always in the offsite operations. So this is just a perspective of production of the crude oil into different products and what percentage of fuel products are made from a crude oil. Now, crude oil has a property and its importance. Now, this is called something crude assay. This is a chart from ExxonMobil. They have published all 100 plus types of crude oil on their website, and it shows that whenever a crude is purchased, a new one, then the refinery have to do a lab analysis to do the crude assay to optimize, to analyze its distillation points and other properties to be able to decide whether the crude is feasible for the process units or not. And Ariel will talk little bit more detail about that. If we check gasoline quality and modes of analysis, we have about 12 plus qualities, and they can be measured either for component and blended product. Now, most of the time they are done by both lab analyzer, but there are some qualities which can be measured by model. So this chart gives you a pretty good idea of what qualities are measured for what component product and whether it's measured by lab, analyzer, or model. Similar chart for diesel qualities and modes of analysis. This is just a pretext for what Ariel is going to talk about. With this, I introduce Dr. Ariel Kegel to go in more detail about different kinds of analyzer. Let me give me the control over.
Suresh, just to be sure, how I deliver between the slides with mouse or with
just mouse? Just mouse.
Okay, excellent. Thank you. Let me try.
Okay.
No, it's not. Just a second. I will try with the keyboard.
Okay, you got it. Yeah.
Okay, excellent. Thank you, first of all, for the analyzer's introduction. And I would like to jump to the best process analyzer management practice based on the ModCon log time experience. Before starting, I would like to emphasize one important point. Model prediction analyzers, or by their other name, inferential, don't perform real measurements, but use the available data from a laboratory or process to calculate the property of interest. Sometimes the relevance of this data is fresh, or it also can be delayed based on the availability of the data. For example, laboratory analysis that was performed 8 hours before, that in comparison to physical analyzers that can be a STM or a correlative analyzer that perform online measurement of the property of interest. And today's presentation will be concentrated on this type of analyzers. So before getting to suppliers and choose one of the proposed solutions, there are actually a few critical factors that shall be considered for analytical method selection and system design. Accuracy and sensitivity. In most cases, especially when we are talking about crude oil analysis, process analyzer measuring method will be different from the laboratory. It's important to understand that the accuracy of different method is not the same like the accuracy that we get from the laboratory. So we may expect some difference in the results. Initial investment and maintenance cost. In many cases, cheaper solution may reveal to more expensive maintenance, which is not considered at the initial stage of the project. Selectivity and interference. Important to understand the complete stream composition, that in order to prevent cross-reference of components. Single or multi-stream applications that mainly related to time measurements and of course to contamination. If there is a need to flush the stream, and what should be the solvent used for that. Sample handling and sample conditioning, this may lead to the complexity of the solution and increase in cost. Reference method and calibration standards, how analyzer will be calibrated. It's something that requires special attention and efforts, and validation procedures, how we may validate the performance of process analyzers, any special tools or chemicals that will be required for that. Basic steps to process analyzer include choosing the analytical method, sampling and sample preparation, proper location and housing, communication to control room, and reporting. Process analyzers, sample prompts, and sample transport lines should be designed to ensure representative and rapid sampling, avoiding the possibility of contamination. Typically, a complete integrated analyzer system and all related services can be provided by experienced system integrators. I'm sure that you're familiar with some and already working with them. Since the process analyzer results must be correlated to the standard laboratory analysis method, it's essential to select the analytical method from many available techniques. Here on this slide, we can see some of such methods, for example, chromatography, surface analysis. We have also to distinguish between ASTM-based analyzers and correlative analysis techniques. It's also important to realize that not all the laboratory methods available for the process. If possible, it's recommended to consider various spectroscopy technologies, which are more reliable and easier to maintain than the other methods. Here, for example, we can see a short list of properties of interest that usually required for raw material like crude oil or final products like jet fuel, gasoline, or diesel. Many of these properties used for process control, and some of them for post-partization, final verification of the product. Each of the mentioned properties has different methods for analysis. For example, sulfur analysis in fuels can be done by a few methods such as UV fluorescence, X-ray fluorescence, or even gas chromatography by using atomic emissions. We will not go into the details of each method and advantage, but on the next slides, we will see a few examples. The most important is to realize that there is no one single solution. In many cases, you will have to make decision of the best method considering the factors that we are discussing on the previous slides. What is interesting to notice that many of the mentioned properties of interest may be measured by the same method. You may see all these properties marked with near the property name. The intention here is to correlative spectroscopy method. It's not a direct method of analysis, ASTM, but this method enables us to reveal a lot of valuable information using the same analyzer. For example, for crude oil analysis, most of the properties can be covered by the same measuring correlative method. only salt and sulfur concentrations require different methods and separate analyzers. Before we go deep into the correlative measuring methods, let's have a look on some examples of standard method analyzers. For example, the most common method for analysis of inorganic salts in crude, it's ASTM D3230 method. It's electrometric method that measures the conductivity of the sample from the process using a mixture of sample, xylene, and alcohol. Although it's an online analyzer, due to the method restriction, it takes about 6 minutes to get a sample analysis. Such an analyzer usually installed on the desalination process, measuring the salt and crude oil content before and after the process in order to optimize the desalination process itself. It's the most common method. That's the same method is also used in the laboratory. There are also other methods of analysis, like using X-ray, but due to some complexities considered to this method, it's considered less popular. Sulfur analysis that correlates to ASTM D2622 and based on X-ray measuring method. Analyzer is very simple in operation. Flow cell going through the analyzer and signal from the transmitted X-ray delivered and detected online. This method all used for high sulfur concentration analysis on a percentage level and cannot be used for low sulfur concentration analysis, typically for the final products. For such a task, it will be required to use some other method. For example, the most common is UV fluorescence method analysis. The sample of interest mixed with air and passes through a pyrolyzer furnace that oxidize sulfur molecules to produce SO2. Then SO2 molecules excited by UV light and decay to lower energy states emitting UV light that is proportional to the total sulfur concentration in the sample. As already mentioned, this method is very common for analyzing the low sulfur content in ppm levels. These were a few examples of discrete analyzers. To summarize this type of analyzers, these are online analyzers that mainly working according to standard method. They provide better correlation with the laboratory, as usually the same method is used in the laboratory. However, if we would like to discuss and emphasize their disadvantages, as you already have mentioned through the previous slides, the response time of these analyzers is usually longer. For example, salt analyzer, it's 6 minutes per measurement. If we're talking about distillation point analyzer based on the D86 method, it can be even 40 minutes. Maintenance is expensive, as contain different parts that have to be constantly replaced. Tubes, syringes, small pumps. Many of them will require consumables and chemicals like carrier gases. So if we have an option not to use this type of analyzers, we will always prefer using alternatives. And what are they? Alternatives, actually correlative analyzers. Correlative online analyzers actually faster. They measure much faster and less expensive. And these analyzers mainly based on the spectrometry measuring method. What does it mean, correlative measuring method? It means that we don't measure directly the property of interest, but measure spectra. It's usually absorbance spectra. And using chemometry, we may build a mathematical model that describes the correlation between the measured spectra and property of interest. Doing such methods, we may find infrared process analyzers, near-infrared process analyzers, Fourier transform, infrared and near-infrared process analyzers, or even, it's not mentioned here, magnetic resonance process analyzers. I assume that you have heard about one of such methods and probably also implementing on your process facility. There is no question what is the best method or analyzer for process analysis. Are all methods considered as complementary techniques that use different regions of the electromagnetic spectrum to obtain information about materials. It's more question of perspective. As here, for example, Fourier transform infrared analyzer mainly used to provide detailed structure information, while near analyzer, near infrared, focused on composition and quantitative analysis. FTIR considered more expensive and complicated solution, and structure information is not our primary interest, as we are looking for a composition. So in many applications, near analyzer, near measuring method will be enough for our purposes. Just to present the difference between both methods, FTIR and near, FTIR uses interferometer, which creates a beam of different frequencies of light. Detector determines how much of that beam absorbed by the sample. This information presented as interferogram, which represents the light intensity as a function of the position of the mirror. Then signal, so-called Fourier transformed, that in order to generate the information we are looking for. The intensity as a function of wave number. On the other hand, near method uses diffraction grating to separate light into desired wavelength. Then this light directed to the sample, and the special diode array detector measures its absorbance. This method contains no moving parts compared to FTIR analyzer, and considered as more stable and require less maintenance. Near principle. So near principle is actually based on the Berlambert law. What does it mean? It means that if we can measure the intensity of the light before it's getting through the sample, and we can measure the intensity of the light after it's coming out of the sample, by referential calculation, we may actually characterize what is the sample, and we can build a spectra, the absorbance spectra of that sample. Just to summarize, what are the advantages of using this method compared to the standard analyzers? First of all, it's low cost of ownership. What does it mean? It means that, for example, if we need to measure some application, let's talk about the gasoline blending. There is a list of something like 7 to 8 different properties that have to be analyzed during the process. All of these properties, for each and every of these properties, if we are going to use discrete analysis, we will need a separate analyzer. We will need a separate analyzer for octane measurement. We will need a gas chromatograph analyzer to measure concentrations of aromatics, benzene, and olefins. We will need a density analyzer. We will need RVP analyzer. Okay, something like 5 to 6 different analyzers, and of course, a sulfur analyzer. And if we are going on the solution which is based on the correlative analyzer, all of these properties except sulfur can be measured by one single analyzer, by one single measuring method. Optimize production processes by real-time monitoring. As we already mentioned, correlative analyzers measure continuously. It means that each and every few seconds, less than a minute, we will have information about the process. Compared to the discrete analyzers, that measured once a period, as already mentioned before. For example, DPA analyzer which measures distillation points based on the ASTM, provides results once a 40 minutes. If we use the same analyzer for more than one single stream, let's say for 3 streams, we will get information once per 2 hours. Is it enough in order to control the process? It's not enough. Therefore, for some properties, it's must to use a correlative analyzer. Improved process knowledge, we already discussed that. Multi-stream capabilities. One single correlative analyzer can simultaneously measure a few streams. Today we will see some solution that can cover 8 streams by one single analyzer. The advantage of that it's possible to install the analyzer somewhere in the middle of the plant, in the middle of the refinery, and putting the measuring cells around the analyzer itself. Distance between the analyzer and the measuring cell can be up to 2 miles, maybe a little bit more. So by one single analyzer, we can actually cover and measure completely different processes by covering the area of 4 square miles. Minimal maintenance required. The one and the only thing that have to be done is to replace the light source. We're also dealing with the spectroscopy and lenses. Maybe if we have a very dirty stream, there will be a need to clean the lenses once a period of time. Easy to calibrate. Automatic calibration software and model updating software. We will discuss about it a little bit later. I will show you some examples. Sample also back to the process. No need for the recovery. The measuring cell is flow through method. It means that the sample can go back and to the process, and no need for flushing. For each and every method, a separate measuring cell can be used. Here on this slide, you can see a few examples of such an installation. The most simple installation you can see here on the left up picture. A very simple sampling system. As you can already see, it contains no electricity. The cable that you can see here, it's a fiber optics. You don't see analyzer installed here because analyzer installed somewhere far away from the measuring cell, from the sampling system. You see very, very simple installation, very, very simple solution. Definitely we can see more complicated installation. You can see here on the back of this enclosure shelter where the analyzer installed, and you can see enclosure which contains seven different measuring cells. It means that streams are actually coming to the analyzer. In the first case, we can see that the measuring cell was installed at the tap point. It means we don't need to bring the stream to the analyzer. We can bring the measuring cell analyzer to the stream itself. A little bit about the mathematical model, so how we will get from measured spectra to property of interest. Models built using chemometry. Chemometrics, it's a chemical discipline that uses mathematics, statistics, and other methods to build a mathematical model that explain the correlation between the measured spectra and real property of interest. Chemometrics approach uses multivariate methods such as POS. POS, it's for partial least squares regression. And it's found as an effective method to be used for correlative analyzers models building procedure. A bit on chemometric principles or how mathematical models are actually built. So mathematical model is a vector. In order to build this vector, it's a file which contains information about the correlation. In order to produce this file, in order to build this vector, we actually need two things. We need spectra from the process and for some specific sample, and we need results from the laboratory. Once we have both results and spectra, we can build a mathematical model. Once we have a mathematical model, we upload this model on the analyzer, and each and every new measurements, each and every unknown spectra, which is multiplied on this model, gives us a property of interest. A little bit about the chemometry, or how the people that doing chemometry are actually looking at the spectra. If I will ask somebody what you are looking here, and these people are actually not involved in the process of model building, he will say, I'll see here 2 peaks, okay? Yes, generally, yes, we see here 2 peaks, but it's not the important information that we are looking for. When we are looking on the spectra, we are not looking on the peaks only, we are looking on the each and every point of this spectra. And once we have this information, we take this information and we put this information inside the matrix. So each and every row in this matrix will be a separate spectra that we got from the analyzer. We have additional matrix, which contains results that we got from the laboratory. While we have these 2 matrices, we actually multiply each one of them, and finally we get a model of interest. We get a model of interest which we can upload on the analyzer. It's very important to understand that model of interest is actually based on the laboratory data. And once we enter into the process of building a mathematical model, it's very important that we will use good quality data. If we will use a good quality data from the laboratory, also our model will be good quality, and definitely prediction that we will produce also will be a good quality prediction. On the other hand, if we will use a bad quality model, it will also affect the results that we will get from the analyzer. Although mathematical models may show very good results, they have to be periodically updated. Model updating not related to process analyzers only, but also to more complicated models used, for example, for process operation in technological units. Models have to be updated in 2 cases. When raw material was changed, for example, we started using a different type of crude oil, or in gasoline blending, incorporated a new stream as a part of the blend, a new stream that we didn't use before. The second case, process was changed, I mean, some changes in the process, which also caused to change a chemical structure of our stream, of our material. Finally, what we are looking for, we actually look for the best correlation between laboratory that uses standard method of analysis and our analyzers. That, of course, if you trust the results of your laboratory, which is must. So one of the biggest concerns related to the process analyzers operators is how they can solve these problems. I mean, how they can make models be always updated, and how they can also control the process of model building if they need, for example, to build or update a model manually. Building or updating a mathematical model is not a complex procedure, but you still need some tools and skills for that. If you are not doing that on a constant base, daily base maybe, and your experience is very low, process of model building may be somehow complicated. As an answer to that problem, there are few available tools on the market that simplify both tasks: software for automatic models update and software for easy model building. As an example, a few screenshots of such a software, just to show the simplicity of the process. Process can be fully automatic, means you just press next button until you get to the desired model. Or such a software also gives you an option for taking more active steps and make some decisions. All is required for the process. I mean, to start the process, it's a list of laboratory data from laboratory analysis, and spectra from the analyzer. During the model building process, software shares with you intermediate results and gives you an option to go back, make changes, and check if better results were achieved. You can also manually exclude outlier or bad samples and decide which samples will be used as a training and which will be used for model validation. That, of course, for more advanced users, but if you are not in the mode of, or if you are in the mode of not making some decisions, you just may leave the process to the software. Such a software also gives you an ability to make an existing model update by incorporating new samples, checking the performance of model in offline regime for development purposes, and much more. To summarize, such a software gives operator a very simple and useful tool for mathematical model operation and maintenance without any need in special tools or skills. Another software that used in the industry in order to keep the process simple and models continuously updated is a software for automatic models update. The principle of operation of the software is very simple. Analyzer linked to the internal plant or refinery database, which contains data from the laboratory. For example, LIMS system. Once new results from the laboratory appears in the database, it's delivered to the software that compares the value with historical data from the analyzer. For example, now we got results that was taken from the process 8 hours ago, and we go to the analyzer historical data, and we compared with the same sample which was measured 8 hours before. And if software see discrepancy in the data, this value used for the model update. A sophisticated algorithm can also identify good data and reject bad data, which is not in line with defined parameters. Telling the truth, such a software is not new on the market, and Modcon itself uses it already for more than 20 years. Here, for example, you can see results of using such a software. During the period of 3 months, between February to April, we can see that the crude, the raw material, was changed twice. What we actually expect to see, we expect to see a discrepancy with between results of the analyzer and the laboratory because the raw material was changed. In fact, we can see, and we can see here a blue dots, it's actually laboratory analysis, and the green line, it's a continuous measurement by the analyzer. And despite of the fact that the raw material was changed twice, we can see a very good correlation between the laboratory data and the analyzer itself. It means the data from the laboratory was used for teaching the model, and based on this information, we can follow after a very good correlation between both. Another example, and you can see here a yellow line, it's a line for the near analyzer and corrected near analyzer, and the blue line here, it's laboratory analyzer. You can see after correction, the results are looking the same. Compared to the orange line, it's actually measurement of near analyzer without any correction. Another example that also can be seen here, you can see a negative bias and positive bias that can be opened during the period of time. And you can see in both cases, the software for automatic model correction actually doing its work very, very good. To summarize, product quality is measured by lab analysis, can be measured by lab analyzers or online analyzers or inferential analyzers. This presentation, we actually could see a different type of analyzers compared between the correlative and discrete analyzers. We could see in this presentation near process technology, and this technology can be used as a very effective tool for many processes inside of our plant or refinery. Near analyzer can also support laboratory. For example, we don't need so much laboratory analysis, and some of the laboratory analysis can be actually delivered to the process. And by this, we can downgrade the capacity, the loading of the laboratory. So the laboratory will be concentrated in more important work, like certification of the final products, passportization. Modern software development allows modeling maintenance to be performed in the house. It means that once you get a near analyzer, you can be responsible and take under the control or the modeling and correction model building process to be done in the house, and not to use expensive and complicated support by third-party suppliers.
Thank you, Dr. Suresh Agrawal and Dr. Ariel Kigel, for a wonderful presentation.
Give me the control back, Ariel.
Oh, sorry. I have to see how I do it.
I think on this thing should be control back. Harsh, can you give me the control?
Yeah, so Mr. Ariel, like on top, you'll see an option, view options. So under
Yes.
that, you can, there will be an option to give up control.
Okay, yes, excellent.
Okay, now got it.
Yeah.
We have now concluded our presentation for Webinar 9. Our Academy has offered monthly webinars on fascinating subjects related to downstream refining operations. The economics and the technology of an oil movement systems will be the topic of our upcoming webinar, the 10th in the Master Series, which takes place on February 21st, 2024. In the next webinar, we will review the oil movement and storage system, why and when it is economical, and various technologies available for the system and economics to justify its implementation. Don't miss it. Remember to set up an account on LinkedIn. We are beginning the registration on LinkedIn on February 1. We will now begin the question and answer session. You can email us any more questions at the email address below and the ones you posted in the conversation. We will ask you 2 poll questions for candid comments following the Q&A session.
I don't have any questions on the chat box unless somebody wants to speak the questions and we can answer it online. If not, then you can also email the question to us, either to Ariel and to myself, and we'll reply you by email. Now, I'll start the two question poll.
Would you kindly take a moment to respond yes or no? First, has your refinery installed a state-of-the-art sampling and integrated online analysis system? Second, did the information presented in this webinar convince you of the benefits of real-time online analysis of required qualities? We will now begin the poll. We will close the poll now. Thanks for participating in the poll. Your answers will give us insight into our webinar content. Our complimentary gift is an ebook with 250 plus pages after you complete the survey. We provide a free 1-hour consultation with our academic director, the webinar presenter, Dr. Suresh Agrawal. Please take advantage of this chance to talk to him about any problems you are having in your refinery or how to sign up with our academy to receive the benefits of eLearning. We hope to see you at the upcoming webinar. When you exit the webinar, it will lead you to the Google survey form where you may provide us with insightful comments. Thank you, and have an excellent remainder of your day or evening.